Hello everyone, in our last class, we studied the motion state of platform diving athletes. We first studied the average speed of athletes during a certain period of time after takeoff and continuously narrowed down the time interval. As the time interval approaches zero, we obtained the instantaneous velocity using both calculation and limit methods, and thus obtained the representation of the instantaneous velocity of t0 at any time. Through this process, we realized that instantaneous velocity is the limit of the average velocity when the time interval approaches zero. From a functional perspective, the average speed of an athlete during a certain time period is the average rate of change of this function during that time period. The instantaneous speed of an athlete at a certain moment is the instantaneous rate of change of this function at that moment. We know that functions can also be represented by graphs. The combination of numbers and graphics is also a common way for us to study function problems. So, what is the geometric meaning of the average rate of change and instantaneous rate of change from the function graph? In this class, we will continue to study the rate of change of functions from a graphical perspective. We take the slope of the tangent at points p0, 1, and 1 where the quadratic function parabola fx equals x squared as an example to study. When it comes to tangents, we are quite familiar with them. We know that if a line and a circle have only one common point, then the line is tangent to the circle. So for other curves, such as parabolic fx equal to x squared, how do we define its tangent at a certain point, such as p0, 1, 1? Let's answer this question first. If a straight line and a curve have only one common point, so is this straight line necessarily tangent to this curve? The answer is probably not really. Let's take the graph of the quadratic function fx equal to the square of x that we are going to study today. If it is equal to 1 with the straight line x, there is only one intersection point 1, 1, but they are clearly not tangent. So turn it around. If a straight line is tangent to a curve, do they necessarily have only one common point? It doesn't necessarily look like it. For example, the sine function fx is tangent to the sine x image and the line y is tangent to 1, but they clearly have more than one focal point. It seems that we can no longer define tangency based on the number of intersection points, as we did when studying the positional relationship between lines and circles. So, how should we define the tangent of the parabola fx at point 1, 1 when it is equal to x squared? We can analogize the research approach from the previous class. In the last class, we studied the instantaneous speed of athletes at a certain moment, such as when t equals 1 second. We first studied the average speed of athletes during a certain period before or after t equals 1 second, such as from 1 second to t1 second. Further reduce the time interval until delta t approaches 0 infinitely. When t1 approaches 1 infinitely, the average velocity will approach a constant infinitely. This constant is the instantaneous velocity of the athlete when t equals 1 second. What does the expression for average velocity mean geometrically? It is the slope of the line passing through point 1, h1 and t1, hd1 on the function graph. We call this straight line a tangent of a parabola. Similarly, let t1 approach 1 infinitely and examine the changes in the position between cuts during this process to see if it also approaches a certain position. This is also the limit thinking of infinite approximation that we learned in the last class. So similarly, in order to study the tangent of the parabola fx equal to the square of x at point 1, 1, we take a point p x and x squared near points 1 and 1 to obtain the secant p0 p. We will gradually move p closer to p0 and investigate the changes in the position of the tangent line p0. We found that when point p approaches p0 infinitely, the position of the secant p0 p will infinitely approach a certain position p0 t. We call this determined position the tangent of parabola fx equal to the square of x at point p0, 1, 1. We have obtained the meaning of the tangent of the parabola at point 1, 1. Geometrically speaking, the tangent of a parabola at point p0 is determined by the tangent line p0 p at this point, and the limit position when point p approaches p0 infinitely. We know that slope is a factor in determining a straight line. Given the known tangent point, if the slope of the tangent can be obtained, the equation for the tangent can be determined. So how do we find the slope of the tangent p0t at points p0, 1, and 1 where the parabolic curve fx is equal to the square of x? We can know from the definition of the tangent mentioned above. The slope of the parabolic tangent p0t is closely related to the slope of the secant p0p. since the tangent is the limit position of the secant. So the slope of the tangent should be the limit value of the tangent slope when point P approaches P0 infinitely. We can use a similar method to the previous class to study. Similar to the previous lesson, we note that the change in the horizontal axis of P0P is delta x. It is not 0, but it can be positive or negative. The abscissa x of point P is 1 plus delta x. The coordinates of point P can be represented as 1 plus delta x and 1 plus delta x squared. We obtain the slope k of the tangent line P0P, which is equal to fx minus f1 minus x minus 1. By substituting the expression for fx and simplifying the expression for point P coordinates, we obtain a result of delta x plus 2. We make the horizontal axis change delta x approach 0 and observe the change in the slope of the secant. When delta x is greater than 0, we can take 1 as the initial value, and then take 1/10 of the previous value each time as the new delta x value to see how k changes. It can be seen that as delta x decreases, the value of k will gradually approach 2. When delta x is less than 0, we also perform a similar operation. It can be seen that as the interval between the horizontal axis decreases, the value of k will also approach 2. Through the demonstration just now, we found that when delta t approaches 0, the slope k will approach 2. The verification through calculation is limited, and like in the previous class, we need to explain this conclusion from a more rational perspective. In fact, from the final expression of k, delta x plus 2, we can directly see that when delta x approaches 0, delta x plus 2 will infinitely approach 2. We call 2 the limit of the equation delta x divided by f1 plus delta x minus f1 when delta x approaches 0 infinitely. Write it as the following expression. Among them, lim represents the limit operation for this equation, and delta x approaches 0, indicating the condition for finding the limit. When point P approaches point P0 infinitely, the secant P0P also infinitely approaches the tangent P0T at P0. The slope k of the tangent line P0P infinitely approaches the slope of the tangent line P0T at point P. The slope ko of the tangent P0T should be equal to 2. We have solved the problem of the tangent slope of parabola fx equal to x squared at points P0, 1, and 1. Can you use the above method to find the slope of the tangent P0T at points P0, 2, and 4, where the square of the parabola fx is equal to x? We will still use the method we just used. The change in the horizontal axis is delta x. The abscissa of point P can be denoted as 2 plus delta x. The coordinates of point P can be represented as 2 plus delta x, 2 plus delta x squared. So, the slope k of the cutting line P0P should be equal to fx minus f2 divided by x minus 2. Substitute the expression of fx and simplify the coordinates of point P to obtain the result of delta x plus 4. When delta x approaches 0, the limit of this equation is equal to 4, so we obtain the following results. So the slope of the tangent at points P0, 2, and 4 of the parabola is 4. After learning how to find the tangent slope at specific points where the parabolic curve fx equals x squared, can we generalize this method? How to find the slope of the tangent P0T at points P0, x0, and x0 square where the parabola fx equals x square? Let's first answer the question, how should we define the parabola fx as equal to x square, and then the tangent at points P0, x0, and x0 square? Just like defining the tangent of a parabola at a specific point earlier, for any point on the parabola, P0, x0, x0 squared is generally applicable. We take a point P near any point P0 on the function graph and construct a tangent line P0P. When point P approaches point P0 infinitely, the secant P0P approaches a certain position infinitely. The straight line P0T at this determined position is called a parabola fx equal to the tangent of x square at points P0, x0, and x0 square. In fact, this is also the definition of the tangent of a general curve at a certain point. So how do we calculate the slope of the tangent of a parabola at points P0, x0, and x0 squared? We will still use the method we just used and keep the change in the horizontal axis as delta x, that is, the horizontal axis of point P is x0 plus delta x. So the coordinates of point P can be expressed as x0 plus delta x, x0 plus delta x squared. The slope k of the cutting line P0P is equal to fx minus fo divided by x minus x0. Substitute the expression of fx and the expression of point P coordinate, simplify and organize to obtain the final result, delta x plus twice x0. The limit of this equation when delta x approaches 0 should be equal to twice x0. So we obtain the following results. That is to say, the parabolic curve fx is equal to x squared, and the tangent slope of points p0, x0, and x0 square is twice x0. We have obtained the definition of the tangent of a parabola at any point and the method for calculating the slope of the tangent. We studied the problem of tangent slope of a function graph at a certain point from a geometric perspective. The research method is very similar to the previous class, both using infinite approximation to reach the limit. So please consider, what is the relationship between the slope issue we studied in this class and the speed issue we studied in the previous class? Observing the function from our previous class, ht is equal to the negative 4.9 times t squared plus 4.8 times t plus 11 in the graph. What is the geometric significance of the expression for average velocity? What is the expression for instantaneous velocity? We can remember point 1, h1 and point 1 plus delta t, where h1 plus delta t are p0 and point p, respectively. From the expression of the average velocity, we can see that the difference between the vertical coordinates of points p0 and p compared to the difference between their horizontal coordinates is exactly the slope of the tangent line passing through points p0 and p. From instantaneous speed, the expression, we can see, limit the expression for average speed. This is also the method we use to approximate the tangent slope with the secant slope. Therefore, the geometric meaning of instantaneous velocity is precisely the slope of the tangent of the function graph at point 1, h1. In this way, we have studied the geometric meanings of the average velocity and instantaneous velocity in the previous class. Finally, let's review the exploration process of this lesson and see what we have learned. From a knowledge perspective, we take parabolas as an example to study the problem of tangent slope in function graphs. We discussed the definition of the tangent of a parabola at a certain point. We know that the tangent line at a point p0 on the function graph is determined by the tangent line p0p at this point and the limit position of point p as it approaches p0. We obtained the slope of the tangent line separately through calculation and limit calculation methods, and thus obtained the expression for the slope of the tangent line at any point on the function graph. Finally, we also realized that in the previous class, the geometric meaning of the instantaneous velocity of the athlete we studied at a certain moment is the slope of the tangent line of the corresponding function graph at this point. From the perspective of research methods, we analogized the research process of the previous class and still used the method of infinite approximation to obtain the tangent slope through the tangent slope. This still contains typical extreme thinking. This is also an important idea, method, and foundation in derivative research. That's all for this lesson. Goodbye, everyone.